Hello everyone, welcome to the series of lectures on the course Calculus and Numerical Methods. In this video, I'll talk about absolute value function. So this absolute value function, it's a function from the set of real numbers to the set of non-negative real numbers. Alright, so this function, what it does is it carries each real number to a non-negative real number denoted by this, and this is read as absolute value of x or modulus of x, and this value which I'm getting here will always be non-negative. It can be 0 and it can be positive. So depending on x, we are going to get non-negative values here. All right, so let's define the absolute value function. For any real number x, we define the absolute value function, or sometimes also called as the modulus function, in this manner. If this x is positive, then we are going to define this absolute value of x to be equal to x itself. All right, and if x is less than or equal to 0, then we are going to define that as minus x. All right, for example, if I look at modulus of 3, 3 is a positive number, so that comes under the first case here. So its absolute value is itself 3. Now let's look at absolute value of minus 7. So minus 7 is negative, it is less than or equal to 0, so it falls under the second case. So its absolute value is defined as minus of that whatever x it is. Alright, so this is minus of minus 7, and that will give you plus 7. And in the same way, we can also talk about modulus of 0. Now, as per the definition which I have stated here, 0 is coming in the second case. All right. Now, what is going to happen when x is 0? When x is 0, you are going to have minus 0 here, and that's 0. Now, some books also put this condition of x equal to 0 here, and they say it is x when x is greater than or equal to 0, and it is minus x when x is strictly less than 0. Both the definitions mean the same, because when you put x equal to 0 here, you are going to get 0 in both the cases. Fine. Some books also give a separate condition: x positive, then it is x strictly negative, then it is minus x, and when x equal to 0, it is 0. Okay, so absolute value of 0, no matter where you keep that 0, either in this condition or in the second condition, that is going to be 0 always. All right, so from here, if I take any positive real number, its absolute value is positive. If I take any negative real number from here, look at this, then its absolute value is again positive. And if I take 0 also, it is 0, right? So this tells us that no matter what real number x you pick up, the absolute value x can never be negative. Okay, so it is defined in such a way that it is always greater than or equal to 0. So that is the first observation that we can make. No matter what real number x you pick up, absolute value of x is always bigger than or equal to 0 for all x in R. And it is going to be 0 if and only if the number x itself is 0. If x is not equal to 0, then absolute value of x is strictly greater than 0, always. Okay. Now, the best way to understand any given function is to look at its graph. Correct? So let me show you the graph of this modulus function. This is the graph of the modulus function. So we have y-axis and the x-axis, that is the xy plane, and for each real number x on the real line, I have plotted the graph y is equal to mod x. So this is a y-axis, the vertical one. The horizontal one is the x-axis. And when x is equal to 0, you can see here in the center of the graph, the value of the function, the dark black line that you can see is 0. And when x is equal to 0.5, it is 0.5 here on the y-axis. Same way when x is equal to 1.5, you can see that it is equal to 1.5. When x is equal to 1, it is 1. So that is going to happen for every positive number here. So the first condition that x is positive, it comes under the right hand side of the real line. So no matter what real number you pick up on the right hand side of 0, its modulus will be itself, right? And if you come to the left hand side of 0, where you get the negative real numbers on the x-axis, you can see that again the absolute value of each negative number is the corresponding positive number. So you can see here minus 0.5 and its absolute value is 0.5 on the y-axis. So the graph of the modulus function, it never comes below your x-axis. So graphically, geometrically, that tells us that the modulus function, it cannot be negative. It can be 0 only at one point, that is at the origin. Otherwise, if you see, no matter how big value of x you take or how small you take, the graph is always going to be above the x-axis. Okay. Now, there is another way of expressing this modulus function, that is in terms of the maximum. And what we will do now is, for each real number x, we will look at the maximum of xn minus x. Okay, so no matter what real number x you take for all x and r, we will look at the maximum of xn minus x. Okay, and we will see that it is equal to mod x. Okay, so what I'll do is I'll take the function y is equal to mod x. Now this mod x, it can be either x or minus x, right? It has two choices. So I will have the lines y is equal to x with me and y is equal to minus x with me. So I have to plot these two lines in my xy plane, and for each x I have to look at its maximum. What is the maximum value that y takes? So let me again show you the graphs of these two lines, y is equal to x and y is equal to minus x. So here's the graph. The red line which you can see here, which is which is in the first quadrant and the third quadrant, and it is passing through the origin, is the line y is equal to x. And the blue line that you can see here, which is in the second and the fourth quadrant passing through the origin, is the line y is equal to minus x, right? So what I'll do now, first let's look at x equal to 0. When x is equal to 0, red line also is at 0 and the blue line is also at 0. So that is the common value it takes. Now let's look at x equal to 1 here. When x is equal to 1, on the red line I get the corresponding value as plus 1. But when x is equal to 1, the corresponding value on the blue line is here down, it's minus 1. And if I take the maximum of minus 1 and 1, that is equal to 1. Okay, so maximum here of the line y is equal to x and y is equal to minus x at the point x equal to 1 is nothing but plus 1. And for each positive number, if you see, the maximum value will be on the red line. That means for each positive real number, I'm going to get this red line here in the first quadrant if I look at maximum of both the functions, right? Similarly, if I go on the second half of the real line, that is the negative side, and again at each real number x, I look at the corresponding maximum value of y. Again, you will see that when x is equal to minus 1, On the blue line, I have here in the second quadrant y is equal to 1. Whereas on the red line, it turns out to be minus 1. So when I take the maximum of 1 and minus 1, I will get 1 again. That means for each negative real number here, the corresponding maximum value of y will be in the second quadrant and it will be on this blue line. So throughout the real line, when I try to take the maximum of these two functions, that will be in the first quadrant and the second quadrant, and that is exactly the value, the graph of the modulus function, right? So graphically, it's quite clear that maximum of x and minus x, that is y is equal to x line and y is equal to minus x line, is nothing but mod x. Okay, and that is going to work for every real number x. So this definition is justified, that mod x, I can also interpret that as maximum of x and minus x for each real number x. All right. Next, we look at some properties of the absolute value function. So let's start with the properties. The first property says, if I take any two real numbers a and b, then modulus of ab will be same as modulus of a into modulus of b. That is, it says absolute value of product of two real numbers is same as product of their absolute values. Fine. So what I'll do is, we will deal with this property. We have to prove it, and we will prove it uh, case by case. So depending on the signs of a and b, okay, we will consider different cases. The simplest case is when one of the numbers a and b is 0 or both are 0. Okay, so case 1 says either a is equal to 0 or b is equal to 0. So let's assume that without loss of generality, I'll assume one of them to be 0, and same thing will work when the other one is 0 or both are zeros. So without loss of generality, I'll assume that a is equal to 0. So if a is equal to 0, then what is modulus of a? That is going to be also 0, right? So what will be the left hand side now? That is modulus of ab. Okay, also from here, because a is 0, a into b is going to be 0 no matter what b is. So absolute value of ab, that will be absolute value of 0, and that is 0. So left hand side is 0. In the same way, what is right hand side? Right hand side is modulus of a into modulus of b. But modulus of a is 0. So this is 0 into modulus of b. I don't know what is modulus of b. It's enough for me that one of them is 0. So the product is 0, right? So if one of them or both of them are zeros, then the left hand side will be 0 and the right hand side will be 0, and the equality is established. So this property works well when at least one of the real numbers a and b is 0, right? Now the second case is when both of them are strictly positive. So let's assume that a is positive and b is positive. So case 2 says, let me put that as case 2. Case 2 is when a is positive and b is positive, both are positive. Now if you see the definition of the modulus function, whenever the real number x is positive, its modulus is the number itself. When x is positive, mod x is x. So both a and b are positive here, so I know that mod a will be positive. Sorry, mod a will be a, because a is positive, and mod b will also be equal to b because b is positive. And because a and b are both positive, their product will also be positive, right? And because their product is positive, modulus of ab will be again ab itself, because the number ab is positive. Now the left hand side, if you see of this expression, that is mod AB. So left hand side is mod AB, but AB being a positive number from here, this is going to be AB because the number AB is positive. By definition of modulus, this is going to be AB, right? And the right hand side of that expression would be mod A into mod B. But from here, because A and B both are positive, mod A is A and mod B is B. So this is also nothing but mod A into mod B. So left hand side is equal to right hand side even in the second case, when one of them is positive and the second one is also positive, when both are positive. Fine. So the first case was wherein at least one of them is 0. Second case is when both are positive. And one more case we can pick up wherein both are negative. Okay, so supposing A is negative and B is negative. So because A is negative, by definition of modulus, if you see, mod A will be equal to minus A because A is negative, and mod B will be minus B, right? Now both A and B are negative. That means their product will be positive because product of two negative numbers is positive. And because this is positive, mod AB will be nothing but AB because AB is positive. So by definition, mod AB has to be equal to AB. So again now left hand side will be mod AB, and that is nothing but AB here because AB was positive. And right hand side similarly is mod A into mod B, but mod A is minus A, mod B is minus B, so this is minus A into minus B. Minus will cancel out with this minus and you are left with AB. So even in this case, left hand side is equal to right hand side. Now the only case that is left is when one of them is positive and the other one is negative. Okay, so supposing A is positive and B is negative, you can also assume the other case wherein A is negative and B is positive. That will work the same way. Fine. So because A is positive, mod A is A, and because B is negative, mod B is minus B. Right? Now A is positive, B is negative, so AB is going to be negative, and because AB is negative, modulus of AB will be minus AB because the term here AB is negative. Now again if I look at the left hand side, that is mod AB, from here it is nothing but minus AB, and right hand side is mod A into mod B. That mod A is A and mod B is minus B, so this is A into minus B, which is minus AB. Again left hand side is equal to right hand side. So we have seen all the cases, all the possible cases for A and B, and a conclusion is that for any two real numbers A and B, mod AB is nothing but mod A into mod B. Okay, so our conclusion is mod AB is equal to mod A into mod B for any two real numbers A and B. This is going to work. Fine. So this is the first property of absolute values. Let's move to the second property. This property says modulus of A square is same as A square for any real number A. Modulus of A square is same as A square for any real number A. So let me pick up a real number. Supposing A is any real number. Now given any real number, we know that its square is always bigger than or equal to 0. Square of any real number is non-negative, right? Therefore, modulus of this number A square is going to be itself because it is greater than or equal to 0. If A is 0, then both the sides will be 0. Otherwise, if A square is positive, then mod A square will be nothing but A square, right? So now I will start with this A square, my right hand side. So now A square is nothing but from here modulus of A square, right? And this a square, I can write it as modulus of a square is nothing but a into a. So I have modulus of product of two numbers. Now if I go back to the previous property, that tells me modulus of any two real numbers product, if you take mod AB, that is mod A into mod B. So if I choose this second A as B and apply the previous property, this will give me mod A into mod A. This is by property number 1, right? And I have mod A into mod A, and that is nothing but mod A the whole square. So what we have done is we have shown that mod A the whole square is nothing but A square for any real number A. No matter what real number A you take, positive, negative, 0, this expression is going to hold true. Fine. Now, if I take positive square roots on both sides, okay, by taking positive square roots on both the sides, what I have is mod A is going to be root of A square. Okay, so this is square root of A square. So whenever I have square root of A square, this is not same as cancelling the square and root and writing that as A. Okay, so whenever I have a square root and a square inside it, that is actually equal to mod A, because this A can be negative. There is a chance that this A is negative, so A square will be positive, and then you are taking its root, right? For example, if I have square root of say minus 3 square, this is how much? 3 minus 3 square is 9, so that is root 9, and this is nothing but 3, right? But this A, if you see here, that is not equal to this 3. Okay, so there is a difference in the sign here. So square root of A square is nothing but mod A and not A. Okay, so this is a common mistake that many people do. They simply cancel out the square and root and they write this expression as A, which is not true. Okay, so this is the second property of absolute values. Moving on to the third property, this says A is less than or equal to mod A and minus A is also less than or equal to mod A. So plus or minus A is always less than or equal to modulus of A. Now we have already seen that mod A is nothing but maximum of A and minus A, right, for any real number A. Now because modulus of A is a maximum of these two, this modulus has to be bigger than or equal to both of them. That's why it is the maximum of this set, right? So modulus of A must be bigger than or equal to A, and modulus of A must be bigger than or equal to minus A also. So if I combine these two inequalities now, what I have, A is less than or equal to mod A and minus A is also less than or equal to mod A. So both of them plus and minus A together are less than or equal to mod A for every real number A, right? A simple property which tells us that the number as well as its negative is less than or equal to its modulus. Okay, so this is the third property. Next one, this says minus of modulus of A is less than or equal to A, and that is less than or equal to mod A. Now again, this is I'll make use of the modulus function here, or we can use the property 3 as well. We know that A is less than or equal to mod A. So by property 3, A is less than or equal to mod A, and minus a is also less than or equal to mod, right? So this implies this inequality, I'll keep it as it is, and to the second inequality I will multiply a negative on both the sides. So because I'm multiplying a negative on both the sides, the inequality is going to reverse, and this will be minus into minus 1 into minus a, that will be a, this will reverse, bigger than or equal to minus of modulus of a. Now if I read it from here, minus of modulus of a is less than or equal to a, and a is less than or equal to mod a. So if I combine both the things together, I can write this as minus mod a is less than or equal to a, and that is less than or equal to mod a. And this is going to work for every real number a. Okay, so this is the fourth property of absolute values. Next one, this says absolute value of x mod x is less than epsilon if and only if x belongs to the open interval minus epsilon comma epsilon. So let me put this on the number line. Supposing I have the number, I'll put this open interval here. I have 0, epsilon and minus epsilon. Now when I say mod x is less than epsilon, that is equivalent to saying that x belongs to this interval minus epsilon to epsilon. Okay, so whenever x lies in this part, its absolute value is going to be strictly less than epsilon. Okay, so let's prove this. So I'll assume this if and only if, so both ways will have to prove. So one way, first way, let mod x be less than epsilon. Okay, so but mod x is maximum of x and minus x. That means this is strictly less than epsilon. If maximum of these two numbers is less than epsilon, then both these numbers are less than epsilon. So this will imply x is less than epsilon and minus x is also less than epsilon because their maximum is less than epsilon. So the biggest one is smaller than epsilon. The other one will be less than the maximum. That also has to be less than epsilon, right? So I can write this as, I'll keep this inequality as it is, and I can multiply a negative again here. So that is going to give me x bigger than minus epsilon. And if I combine both of them, I'll have minus epsilon is less than x, and that is less than epsilon, and which is same as saying that x belongs to open interval minus epsilon to epsilon, right? Because x belongs to minus epsilon to epsilon, that means x belongs to the open interval minus epsilon to epsilon. So we assume the first part and we show that the second part is true. Now conversely, what you can do is you can assume the second part. Okay, the last step, you'll start with this. If x belongs to this interval, that means minus epsilon is less than x is less than epsilon. That means you can come to this step. Actually, what you can do is you can, from here only you can convert this implies into implies and implied by, and you can keep on moving step by step upwards, and that will give you the proof for the opposite one. So I can do it in one shot actually. Okay, so that's what I have. You can also write it in two ways actually. Okay, so you can do it one way, and after you finish this, from here you keep on moving upwards. Now another thing that you can do from here is you can have less than or equal to here also, and whenever you have less than or equal to here, this interval is going to be a closed interval instead of an open interval. Okay, so how that will look is mod x is less than or equal to epsilon if and only if x belongs to the closed interval minus epsilon to epsilon. So in a similar manner you can prove this as well. Okay, the next property, property number 6, this property is just an extension of the last property, that is property number 5. Okay, so what this says is modulus of x minus a is less than epsilon if and only if this x belongs to the open interval a minus epsilon comma a plus epsilon. So if you visualize this on the number line, supposing I have a point A somewhere and I have the interval, you add some positive epsilon to this, so that will give you A plus epsilon, and you'll have A minus epsilon. So you are having this open interval. Fine. So the point x will come in this interval A minus epsilon comma A plus epsilon if and only if the absolute value of x and A is strictly less than this epsilon. Okay. So this is what we need to prove, and the previous one was actually a special case of this when A was equal to 0. So if you put A equal to 0 here, you are exactly getting property number 5, right? So let's assume that mod x minus A is less than epsilon. Now you can think of this number as your x, and that is less than epsilon, right? So by property 5, this is going to happen if and only if minus epsilon is less than x minus A, and that is less than epsilon. So this is by property 5 on the previous slide, correct? And that is going to happen if and only if, what I can do now, I can add A throughout this inequality. So I'll add A here, and A here. So when I add here to the central part here, only x will be remaining because A will cancel out with minus A. So if I add A throughout, I have this with me, right? So this is by adding A throughout. That means x lies between A minus epsilon and A plus epsilon. And by definition of an interval, x belongs to this open interval A minus epsilon, comma A plus epsilon. And we have this result. So mod x minus A is going to be less than epsilon if and only if x belongs to A minus epsilon, comma A plus epsilon. Okay, so these are very important properties which we will be using in the upcoming lectures. All right. So these were the first 6 properties. We will look at the remaining 3 properties of absolute values in the next session. All right. And these are my references. Thank you.